Welcome to week 3, Mathematics for Machine Learning. Day 1 will be looking at linear algebra fundamentals. Day 2, advanced linear algebra concepts. Day 3 will be covering calculus for machine learning, which will cover specifically derivatives. Next, on day 4, we'll be doing again calculus for machine learning, but this time with integrals and optimization. For day 5, we'll be looking at probability theory and distributions. For day 6, we'll be looking at our statistics fundamentals. Finally, on day 7, we'll be doing our math-driven mini project on linear regression from scratch. Welcome to week 3, day 1. Today, we are going to cover linear algebra fundamentals, one of my favorite topics in school, and I hope you enjoy this one. First, we're going to look at vectors and matrices. Now, what is a vector? A vector is a 1D array representing quantities with both magnitude and direction. It looks something like this. Example, more like a list format. Then we have a matrix. A matrix is a 2D array of numbers arranged in rows and columns. One of the example is this, where we have a 3 by 3 matrix displayed here, where its values are 2, minus 3, 1, 2, 0, minus 1, 1, 4, and 5. It's kind of, you read it out from left to right, and then you go down every single row. Let's talk about the properties. As I mentioned, the matrix is kind of read out as 3 by 3 or m by n, where m is the rows and n is the columns. A vector, on the other hand, is a special case of a matrix with one row or column. As you can see above, we have a list 2, 3, and 4. That's a matrix with only one row or column. Now let's go ahead and talk about matrix operations. We have addition and subtraction first. Matrices must have the same dimensions. For element-wise operation, I can give you an example. What we can do is we can create a new file, Python, save it as week 3, day 1. I want to make sure I'm in the right folder, day 1 underscore samples. Here, I am going to first import NumPy. If you have not gone through week 2, I would probably recommend you go to week 2 to understand whatever we are doing, because we'll be using NumPy quite a lot. I'm going to create a matrix here by using np.array, and in here I'm going to make a 2 by 2 matrix, 1, 2, 3, 4. So I have my 2 by 2 matrix here. Similarly, I'll create one more, call it B, and here I'm going to add values a little bit more than that, 5 by 6 and 7 and 8. So I have my two matrices here. One is A and one is B, and the values are 1, 2, 3, 4, 5, 6, 7, 8 for these two matrices or two variables that we created, A and B. Now if I want to print the addition between the two of them, I can directly say A plus B, because these are NumPy arrays, so I can directly use that. Similarly, I can also do subtraction by saying A minus B, and it does, as I mentioned, element wise addition and subtraction, which means it will take each element and take the corresponding one to it and do the operation. So if I run this, let's open my week 3, day 1, perfect, Python day 1 samples, and it will give you the solution here, 6. Okay, it's always good to put it on the next line so it looks much more clear. Clear it out, run it one more time. I have 6, 8, 10, 12. So 5 plus 1, 6 plus 2, 7 plus 3, and 4 plus 8, 12. Similarly, 5 minus of 1 minus 5 is negative 4, 2 minus 4, 6 is minus 4, 3 minus 7 is minus 4, 4 minus 8 is minus 4, and that's why we have this subtraction here. I can always do other way around. So it's all positive numbers, 3, 4, 4, 4, 4. So you can always do element-wise operations for addition and subtraction. Next, we want to talk about scalar multiplication. Now, this is not a matrix multiplication. That's something else we will talk about. But scalar multiplication is you multiply every element in the matrix by a scalar. So what happens in that case is, so for example, I want to create an array C, which is 2 times A. So this is where you give a scalar value to a particular matrix. And now if I print it out, multiplication slash n comma c. So what this does is it does something similar to addition, but it will take the value 2 and multiply with every single element inside the matrix A. So if I run this, I have 2, 4, 6 and 8, because 1 times 2 is 2, 2 times 2 is 4, 3 times 2 is 6, and 4 times 2 is 8, and that's what we get in scalar multiplication. Another operation that we have, which I want to talk about, is matrix multiplication. It requires the number of columns in the first matrix to be equal to the number of rows in the second matrix. So because of the way the multiplication works, so it's, you have to remember again, number of columns in the first matrix to be equal to the number of rows in the second matrix. The reason is the formula for this goes something like this. Let's say A and B are two matrices, and I and jth element of A times B should be equal to summation of n equal to 1 to k, A ik and B kj. So if you see, the rows and columns kind of multiply with each other. That's why the number of columns in the first matrix should be equal to the number of rows in the second matrix. Now if you want to use it in Python, the way we do it is A equal to np dot, let's say we already have the array, so I'm not going to create again, I'm going to just use them. Let's say result equal to np dot, the function is called dot itself, a comma b. So this is what this does, is it will multiply a and b together. I can say print matrix multiplication slash n and pass the result there. Run it. I'm gonna comment out the rest of them and just run this. So looks like I have the wrong answer here because I have said A and C. Let me do A and B so it's much more visual. So I'm going to go here, clear it out and run it again. So there you go. We have 1 times 5, which is 5, plus 2 times 7 equal to 14. 14 plus 5 is 19. That's the value here. Same thing. So you keep on doing multiplication by rows by columns, and that's why you get this solution here. So again, the first element in the row with the first element in the column, first column, second element times the second in the row times column, say first element, that is the first element right here. So similarly, you keep on going through these elements one by one, and then you do that. But again, luckily you don't have to do those manually. You can just use np dot function. Now it would be so much easier if it was available when we were in school, but again, we had to learn this the hard way. So next thing that I want to talk about is special matrices. So under special matrices, we have identity matrix, which is I, a square matrix with ones or on the diagonals and zeros elsewhere, and it's represented as I times A equal to A. The way we do that in here in our code is we say I equal to np dot ey 3 by 3. If I want to print this, print to see how identity matrix look like, identity matrix. Now again, I didn't have to specify 3 by 3 because, as I mentioned, it's a square matrix. So if you just have to provide one, and it will one element of what the row is, and columns is the same as the rows. I am going to run this up, and there you go. We have 1 0 0 0 1 0 0 0 1, and if you see, the diagonal elements are all 1. Similarly, I can make it a bigger one. There you go, 1 1 1 1. So all the diagonal elements. So that's an identity matrix. I am going to show you another one, which is a zero matrix. A zero matrix is a matrix with all the elements as 0. So this doesn't have to be a square matrix. For this, I am going to comment this out. Let's move it a little bit up. And a zero matrix looks like, let's say, z equal to np dot, and to create that you say zeros, and then you have to specify the rows and columns. So let's say if I want to create 2 by 3, I can say print 0 matrix slash n comma z, save it, go back, clear it out, and let's print it out. So 0 matrix is a 2 by 3 matrix here with all zeros inside here. That's what a 0 matrix look like. Next thing that I want to talk about is a diagonal matrix. A diagonal matrix is a square matrix where all elements except the diagonals are 0. So it's a little bit different than identity matrix. Again, it's a square matrix, but in this case everything except the diagonals are 0. So the way you create them in Python is use the numpy, say diag, and now here I'm going to give some values 1, 2 and 3, and let's print this diagonal matrix slash n comma d. Let's look at how it looks like. Let me go ahead and first comment this out, open this, clear it out, make sure it's saved, run it. And if you see here 1, 2 and 3, so when you say diagonal matrix, you're actually giving the values to the diagonals. So everything except the diagonals are 0 in this particular case. So that's a diagonal matrix. Now next, now that we understand all the different types of matrices, let's go and play around with them. Let's head to hands-on exercises. So our first exercise is to create vectors and matrices using NumPy. So just to get started with things. Our objective here is to practice creating and manipulating vectors and matrices. First, let's create two matrices of size 2 by 2, and then we'll perform addition, subtraction, and scalar multiplication. So let's go back here, clear this out. I'm going to create a new file called as day1 underscore exercise 1.py. As I mentioned, first, we always need numpy as np, and as I mentioned, our first step is to create matrices. Our first matrix will be np.array, and inside that I'll create 1, 2 and 3, 4. Nothing special. I'm going to copy this and create another one called as b, and here I'm going to say 9, 8, 7 and 6. Okay, so I've created two matrices. Now next, first thing is addition. So try to pause it here and do it yourself, and then continue. Print addition. So if you got it right, you probably did something like this where you said a plus b. Simple enough. How about subtraction? So try to do subtraction and then come back, and then next thing, as I mentioned, you can do a scalar multiplication with the number 3 for the matrix A. So try that and then come back. So if you did it right, you probably did print subtraction slash n comma a minus b. For scalar multiplication, I mentioned that do slash n, do a multiplication of 3 times the matrix A. So if you did exactly like this, it should show up something like, let's clear it out, Python day1 underscore ex1.py. So we'll get 10, 10, 10, 10 because 9 plus 1, 8 plus 2, 7 plus 3 are all 10. Subtraction, 1 minus 9 is minus 8, 2 minus 8 is minus 6, 3 minus 7 is minus 4, and 4 minus 6 is minus 2. And then scalar multiplication for A, 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 9, and 3 times 4 is 12. So that's what you should see as the output of exercise 1. We have exercise 2, where we will be implementing matrix vector multiplication. So the objective here is to multiply a matrix by a vector. So first we'll create a 3 by 3 matrix and a 3D vector, and then perform matrix vector multiplication. So let's see how do we do this in code. If you want to try it out, you can try it out yourself before you look at the solution. I'm going to call day1 ex2.py. Here, first, we need to import numpy as np. Next thing is we'll create a matrix and vector. So for the matrix, I'm going to call it m equal to np dot array, and as I mentioned, we're going to create 3 by 3. So I am going to give it numbers 1, 2, and 3. Our next row is 4, 5, and 6. Our next row is 7, 8, and 9. So it's a 3 by 3 matrix here. Now we need to create a vector. I'll call it v equal to np dot array, and my vector is always one row or one column. So I am going to call it create one row matrix 1, 0, and -1. Now let's do a matrix vector multiplication. So to do that, I am going to say matrix vector multiplication, and here I'll create a result array, result matrix np dot m comma v. Now if you use the same numbers, our multiplication results should be same. Print matrix vector multiplication slash n comma result. So let's display it and let's see if we have the same answers. I'm going to clear this out. Let's say python day1 underscore exercise 2 dot py, run it, and our matrix vector multiplication is -2, -2, -2. It's kind of did the multiplication based on these two vectors, and this is the solution that you should be looking at. If not, check your code again and then go through it again. For today, we have an extra. We have exercise 3, where we will explore special matrices. So objective here is to work with identity, zero, and diagonal matrices. So what we'll do is we'll create a 3 by 3 identity matrix and multiply it with another matrix, and then create a diagonal matrix and a zero matrix. So let's go ahead and do this. I'm going to clear this out, save it, and create another one. This one I'll save as day1 ex3.py. Now here, as I mentioned, first we'll create an identity matrix. So I'll let you guys do that. Next, do a diagonal and zero matrix and display them out. So that's what you have to do. So if you have already done or not, just pause it and come back. So first thing that we need is import numpy as np. Next, for identity matrix, I'll say I equal to np dot I, and I will create an identity matrix of 3. It's up to you, whatever you create. And then I'll create another matrix np dot array. Now if I want to do a matrix multiplication with identity matrix of 3, I need to make sure the rows are matching with the columns, which means I'll create a same 3 by 3 matrix 1, 2, and 3, comma 4, 5, and 6, comma 7, 8, and 9. So my 3 by 3 matrix. Next, let's do the multiplication. I'm going to say A times I slash n is np dot and A comma I is what I'll pass. Let's run this and check if it works. Python day1 ex3.py, and there you go. We have a matrix 1, 2, 3, 4, 5, 6, 7, 8, 9. The thing is, as I mentioned earlier in our previous slide, where identity matrix I times A equal to A, identity matrix always gives you the same result as your as your original matrix. So there you go. So that's success. Next thing that I want to do is create a diagonal matrix. So I'm going to create a diagonal matrix np dot diag, if you remember that. And then I'll create 1, 7, and 9. Some random numbers I'll give this time. Then I'm going to say z equal to np dot zeros. This time I'll create 3 comma 3, 3 by 3, and let's print first the diagonal matrix slash n comma d. Next I want to print the zero matrix, so I'm going to call it zero matrix with z. I will comment that out. I don't want to see that, so let's go ahead and print it out. And there you go, we have a diagonal matrix 1, 7, and 9. The values are in the diagonals, and zero matrix of 3 by 3. We have a zero matrix of 3 by 3 here. I hope you were able to follow along or do these on your own. If not, let me know and I can help you out. Our next step is some additional practice for you. Try this out. First thing that you want to do is compute the determinant and inverse of a 2 by 2 matrix using NumPy. Next, try to verify properties of a matrix multiplication. Something like a times b raised to t equal to b raised to t and a raised to t. Then create a block diagonal matrix using NumPy. Try this out and let me know if it works. If you have any questions or problems, let me know and I'll come back to you. So just to summarize, today we learned the foundation concepts of linear algebra, including vectors, matrices, and operations. These concepts are crucial for understanding machine learning algorithms and computational models in AI. So if you have any questions, welcome back to day 2. Today we are going to look at advanced linear algebra concepts. Yesterday we looked at some of the linear algebra concepts. Let's look at something more. So here we're going to cover first determinants and inverse of a matrix. Now, what are determinants? A determinant is a scalar value that provides information about a matrix's properties, such as invertibility. It is calculated only for square matrices. Some of the key insights for the determinant include: if a determinant of a matrix A equal to 0, the matrix A is singular, which means it's not invertible. Whereas if determinant of A is not equal to 0, then A is invertible. Let's look at the geometric interpretation for that. So for a 2 by 2 matrix, the determinant represents the scaling factor of the area formed by its column vectors. So the formula can be represented for a 2 by 2 matrix as determinant of the matrix is, here we have a 2 by 2 matrix A, B, C, D, equal to A times D minus B times C. That kind of gives you the determinant of a 2 by 2 matrix. Now let's look at how we can implement this inside Python. So I'm going to start a new file, Python. I am going to save it inside my day 2 and call it samples. Here, let's start with importing NumPy as np. So I have that available. Now I'm going to say create a matrix np dot array, and then let's create a matrix here 2 by 2, call it 2 comma 3 and 1 comma 4. Now if you look at our formula that we have given here, if I try to calculate a times, sorry, 2 a, so this is a, b, c, and d, ad, which is 2 times 4, 4 to the 8, and then 3 times 1, which is 3, 8 minus 3 is 5. So let's go ahead and calculate that and see if it gives me the determinant. Determinant equal to np dot linalg dot determinant of A. That's where it's available. So linear algebra dot determinant, print what is the determinant of this. I can get that by printing this out. Let's go ahead and check it out. Python day underscore samples. I forgot to put the day 2. So as I mentioned, it's 5.00001 because it has a little bit of error factor over there, but that's perfect. It's multiplying by float, so we get sometimes this thing, but the value is 5. Now let's look at next topic, which is inverse of a matrix. So the inverse of a matrix A is denoted as A raised to minus 1. That's how you can tell if a matrix is an inverse matrix. Now the product of a matrix and its inverse is the identity matrix, which kind of makes sense. A reverse of itself is identity matrix. A matrix is invertible only if the determinant of A is not equal to 0. Now a formula for a 2 by 2 matrix shows something like this: A raised to minus 1 equal to 1 divided by determinant of A and the matrix D minus B minus C A. That's how you can get an inverse matrix. So how do I implement this in Python? I can go here. Let's go ahead and comment this out. I'm going to say inverse equal to np dot linear algebra library dot inverse of A, and I can print this one saying inverse of A is slash n comma inverse. Let's look at how the inverse looks like. Clear this out, run it again, and here is my inverse of this matrix. So this times this matrix should give us an identity matrix. Next, let's look at eigenvalues and eigenvectors. Now, what are eigenvalues and eigenvectors? Eigenvalues and eigenvectors are properties of square matrices that describe transformations. So for example, if a matrix A times V equal to lambda times V, then in this particular case, the V is the eigenvector, a vector that doesn't change direction during the transformation. And lambda is an eigenvalue, a scalar indicating how V is scaled during the transformation. The geometric representation of this, I can talk about eigenvectors as an eigenvector point in the direction where the matrix transformation stretches or compresses vectors, whereas eigenvalues indicate the factor of stretching or compression. The properties I can talk about is a matrix of the size n by n has n eigenvalues and eigenvectors. Eigenvalues can be real or complex, and another property is for a symmetric matrix, eigenvalues are always real. Now, let's see how we can compute eigenvalues and eigenvectors in NumPy. So I'll go back here. I'm going to use the same one. I'm going to comment this out. You can say eigenvalues, comma, eigenvectors equal to np dot linear algebra dot eig of A. This will give me the eigenvalues and eigenvectors for matrix A. If I want to print it and check it out, I can say print eigenvalues slash n comma eigenvalues. Can do the same thing for eigenvectors. I can print this out here. So let's go ahead and run this and check it out. So eigenvalue for that matrix is 1 and 5, and eigenvector is this particular matrix right here. I can give another example. So for example, if we create another array, let's call it B because A is already there. np dot array, give it values 4 comma 2 and let's create 1 comma 1. Now I can say eigenval and eigenvec equal to np dot linear algebra of dot eig of B this time, and then I can print eig val is comma eig val, and for vectors, since it's a matrix, I'm going to go into next line and display this here. Comment this out because we want to see for B here. Clear it out and run this again. And this is my eigenvalues and this is my eigenvector here. So they are available. So this is how you can calculate eigenvalues and eigenvectors in NumPy. Next, I want to talk about introduction to matrix decomposition. Now first, what is matrix decomposition? Matrix decomposition is a process of breaking a matrix into smaller components to analyze or solve problems. Now for that we have singular value decomposition or SVD. SVD decomposes a matrix A into three matrices. We could get A equal to U times sigma times V raised to T, where U is a left singular vectors or orthogonal matrix. Sigma is a diagonal matrix of singular values or non-negative. V raised to T is the right singular vectors or orthogonal matrix. Now, some of the applications of SVD include dimensionality reduction. Example, in principal component analysis, PC algorithm, we use that. We also use it for noise reduction in data sets and also sometimes for image compression. Let's look at how we compute SVD in NumPy. So I am going to comment this out. I will use my A matrix. So I'm going to just write some code here so it's visible to you. U for sigma I'll use S and V raised to T I'll say VT equal to NP dot linear algebra dot SVD. So if you see, you don't have to write any of these, implement any of these functionalities. They're all available as part of NumPy linear algebra library. Now let's print them out. How is it decomposed of? U is slash n U. Same thing I'm going to do for S is S and V or V raised to T is sometimes called as V transpose. So if you want to know the full form of that, VT. And S is also sometimes called as singular values. So that's what it is. So as I mentioned, U is the left singular vector. This is S is the diagonal matrix of a singular values, which is non-negative. And this is the right singular vectors, which is also called as V transpose. So let's go ahead and clear this out, run it out, and you have your U matrix, a singular values, and the V transpose right here. And these together kind of create the matrix A. Now, next step is to jump into hands-on exercises. Here, first exercise that we will be covering is calculating the determinant and inverse of a matrix. We learned this in the first section today, where the objective is to practice using NumPy to compute determinants and inverses. So instructions that will follow here is we'll create a 3x3 matrix and then compute its determinant and inverse. So it's pretty straightforward. So let's go create a new file. I'm going to save it as day2.ex1.py. In here, I am going to first import NumPy as np. Next, we'll create an array A, np.array or a matrix which is 3x3. So I will create it this way. I'm going to say 2 3 1 comma 4 5 6 some random numbers. I'm just filling it up. 7 8 9. Okay, so this is my matrix. Now to create the determinant, I'll say determinant equal to it's np dot linear algebra dot determinant of A. Similarly, for inverse, I will say np dot linear algebra library dot inverse of A. That's it. Pretty straightforward. Let's print them out and check it out. Our results. Determinant determinant inverse is inverse. Let's go ahead and run this. I'm going to say Python day2.ex1, and there you go. We have our determinant and we have our inverse. Pretty big numbers I see here, exponential raised to ex, so that means the decimal places are pretty low. But here we have our determinant and inverse, and we can use these. Now let's jump into exercise 2. Our exercise 2 is to compute eigenvalues and eigenvectors. So the objective here is using NumPy to compute and interpret eigenvalues and eigenvectors. So we will be creating a 2 by 2 matrix and compute its eigenvalues and eigenvectors. Pretty straightforward. So let's go ahead and create a new file, day2 underscore ex2.py. Here first thing is import numpy as np. Next, let's create a matrix A equal to np dot array, and as I mentioned, I'll create a 2 by 2 matrix. So this matrix will have 4 comma, it's a negative 2, 1 comma 1. So this is my matrix. Eigenvals and eigenvectors equal to np dot linear algebra dot eig of a. Now let's print this. That's it. Eigenvalues, don't have to eigenvectors. So I'll say eigenvalues, comma, and eigenvectors slash n, because it's a matrix. This is a singular. So I'm going to clear this out, and I'm going to say Python day2 ex2, and there you go. We have our eigenvalues and eigenvectors. Let's do one more exercise, and in this one, let's perform the singular value decomposition. So we'll be using the SVD function in linear algebra. The objective here is to implement SVD and interpret the components, which is the U, sigma, and V transpose. So let's go ahead and code that out. Create a new file, save it as 3. Here, import numpy as np. Next, a equal to, let's create a matrix, np dot array. I will create a 3 by 3 matrix here. First values, let's give some random values, 3, 1, 1, comma, next one, I'll say -1, comma, 3, comma, 1. Next one, I'll create 1, comma, 1, comma, 3. So I have my matrix here. I can get U, S, and VT from np dot linear algebra dot svd of this matrix. So let's print them out. Print U slash n, print me U. Next, single values. So this is singular values, which is diagonal, and that is S, and this one is V transpose, which is VT. Now if I want to reconstruct the matrix and see if it works, what I can do is, let's say reconstruct, because someone asked me that can you use all these 3 and then reconstruct. So I can say sure, sigma equal to np dot zeros, create a zeros matrix 3 by 3. Then I want to do np dot fill underscore diagonal with sigma with s. So that kind of creates my initial thing. Then reconstructed constructed equal to u at the rate, so multiplication pretty much, sigma multiply that with V transpose. So that should be my entire matrix. So let's print it out. Reconstructed matrix slash n is reconstructed. Okay, perfect. So let's run this up and then check if it matches what we have here. So I'm going to say Python day2 x3. Okay, there you go. Our first U matrix, our S sigma, which is singular values, and V transpose. Now we took the singular matrix and then we created a zero first, and then we uh, filled the diagonal with the values that we have, and then we created the reconstructed matrix using the U, sigma, and VT, which is 311 minus 131 113 exactly to the dot. So there you go. That's how you can create create a decomposition matrix, singular value decomposition matrices, and then reconstruct them back here. Now, for some additional practice, you can try to compute the eigenvalues and eigenvectors for larger matrices. You can use SVD to reduce the dimensionality of a dataset, and also try to verify the properties of an eigenvalues. You can do the determinant of A minus lambda of identity equal to 0. Try that out and let me know how it works. If you have any problems or had any problems following along through any of these exercises or any of the additional practice that you're doing, let me know and I'll get back to you. So just to recap, today we learned advanced linear algebra concepts including determinants, matrix inverses, eigenvalues, eigenvectors, and matrix decomposition. These concepts are foundational for understanding data transformation and dimensionality reduction techniques in AI. So if you had any issues or problems, day 3. Today we are going to look at calculus for machine learning. Specifically, we're going to look at the derivatives. So first, we're going to cover introduction to derivatives and their role in optimization. So what are derivatives? A derivative measures the rate at which a function changes with respect to its input. For a function f of x, the derivative, or also called as the first derivative, f of x, indicates the slope of the tangent line at a point x. Let's look at the role in optimization for derivatives. Derivatives are used to minimize or maximize a function, which is critical in machine learning for optimizing loss functions. Example can be the loss function in linear regression measures the error. Derivatives help find the direction to adjust parameters to minimize this error. So let's look at some of the common derivatives. We have for f of x equal to x square and the first derivative is equal to 2x. And for f of x equal to sine x and the first derivative equal to cos x. Now how do we implement this in Python? Using, we have a library called a SymPy. So I'm going to start with the Python file, save it in our day3 underscore samples. And here I'm going to use that SymPy library as SP. And here I'm going to say x equal to sp dot symbol. And for that, I'll use x. Next, f equal to x star star 2, squares that up. So that's our f of x equal to x square, which we mentioned right here. And now to get the derivative, I am going to say sp dot diff and pass it the two variables f and x. Let's print the derivative. There you go. Save it, open and make sure we're in the right place. Python day3 samples. And there you go. Derivative is 2 times x, which is what we are expecting right here. So similarly, you can do that for the other one too, but I'm going to leave that for you. We're going to jump into partial derivatives. Now, a partial derivative measures how a function changes with respect to one variable while keeping the other variable constant. So for f of x equal to x square plus y square, partial derivatives are defined as its partial derivative of f divided by partial derivative of x equal to 2x and partial derivative of f divided by partial derivative of y equal to 2y. We also have gradient where the gradients is a vector of all partial derivatives, indicating the direction of the steepest ascent. For f of x equal to x square plus y square, the gradient is defined as del of f or nabla of f with the matrix of partial derivative of f divided by partial derivative of x and partial derivative of f divided by partial derivative of y, which is equal to 2x and 2y. That's the matrix of 2 by 1. Now in Python, how do we implement these things? Whatever we did partial derivative and gradient. So let's see how do we get the partial derivative and gradients here. I'm going to go clear this out. Here I am going to say a comma b. Actually, let's keep the values as x and y only. So x comma y, we can get it by saying sp dot symbols that I want to use in this particular case is x and y. So that's what we get assigned here. F equal to x square of 2 plus y square of 2. It's exactly same as the function that we have here, x square plus y square. So that's what I'm doing here. Next, I'm going to say gradient of x equal to sp dot def f comma x and gradient of y equal to sp dot def differential f comma y. So now let's go ahead and print the partial derivatives that we created. Partial derivatives, and I can pass grad x and gradient y. There you go. Oh, I spelled it wrong. That's why it was not showing up. And there you go. Let's run this and check out the solution. And there you go. Partial derivatives is 2 times x, 2 times y. That's our object that we wanted to get. So this is how you can implement this using Python. And SymPy is the library that we use. Next, look at gradient descent optimization algorithm. Now, what is gradient descent? Gradient descent is an iterative optimization algorithm used to minimize a function. Example can be a loss function. It updates parameters in the direction of the negative gradient to find the minimum. Now the update rule here is theta equal to theta minus alpha del or nabla f of theta, where theta is parameters of the model and alpha is the learning rate, which is the step size. Now, why is gradient descent important in machine learning? It's used in training models to minimize the loss functions and find optimal model parameters. And that's why it's very important to understand how this works. Now, let's go ahead and jump directly into our hands-on exercises. So our exercise 1 is to compute derivative of basic functions. So objective here again is to use Python to compute derivatives of simple functions. First, we'll define a symbolic function using SymPy, and then we'll compute its derivative. Something that we did already, but let's do it as an exercise. Follow along if you want to. If not, if you want to do it before me, just go ahead and implement it and then cross-check your answer. So I'm going to say day 3 underscore exercise 1. I wanted to make it as a, so I'm going to open again, open dot, and make sure that I make it a Python file, add and open that file. Okay, so here first import SymPy as sp. Once I have that, let's go ahead and define a function. I'm going to write comments so you can understand what I'm trying to do. X equal to sp dot, let's create a symbol. Let's use our traditional x symbol. Next, I'm going to create a function x raised to 3 minus 5 times x, 5x plus 7. So now if I want to get its derivative, let's compute the derivative of this. That I can do by saying, let's say derivative equal to sp dot def f comma x, and this should give me the function. So I can get the initial function, function, which is f. I am going to print the derivative of it, which is the derivative. Let's look at the function and its derivatives. Clear it out. Python day 3 exercise 1.py, and here is the function x cube minus 5x plus 7, and the derivative of that is 3 times x square, or 3x square minus 5. So that's the derivative of this function. Pretty easy, and Python helps you, makes it much more easier. Our next exercise that we want to look at is computing the gradients. Here the objective is to calculate partial derivatives and the gradient for a multivariable function. What we're going to do here is we define a function with two variables, and then we'll compute the partial derivatives and represent the gradient as a vector. So let's go ahead and implement this. Create a new file. I'll call it day 3 exercise 2.py. First, let's go ahead and import our SymPy. Next, I am going to define a multivariable function. In the previous one, we just used x. This time, we're going to do both x and y. So x and y equal to sp dot symbols. I need x and y. These are the symbols that I need. So that's what I specified. My function in this case is, let's say, x square plus 3y, so 3 times y square is this way, and then I'll say minus 4 times x times y, so 4xy. So this is represent f is equal to x square plus 3y square minus 4xy. Now let's go ahead and compute the partial derivatives. You can say grade, or I can first write the comment, said compute partial derivatives, and to do that, grad underscore x equal to sp dot def, and I give my function and variable x. Next, for grad y, I will say sp dot def, and I'll say f comma y, function y. So that's perfect. Now let's go ahead and print our gradients. So our first gradient f of, let's say, the function for grad x, or let's say grad x, I'll keep it simple. I don't want to say a differential of grad x, but that is grad underscore x, and I have similar for grad y is grad underscore or gradient y. So there you go. Let's go ahead and run it. I'm going to clear this out, and this is exercise 2.py, and here you go. So for our function x square plus 3y square minus 4xy, our gradient x, or the partial derivative, is 2x minus 4y, and our gradient y is minus 4x plus 6y. I hope you were able to do it, but we're going to move to the third one, which is implement gradient descent for linear regression. Now the objective here is to write a Python function to perform gradient descent and optimize parameters for a linear regression problem. So we can use NumPy for this one because we have the solutions available for it. We're going to define the gradient descent function, and we're going to provide some sample data and perform the gradient descent. So let's go ahead and implement this. I'm going to say this is exercise 3, and here first I am going to import NumPy as NP. Next, the first step that I mentioned is we will define the gradient descent function, and that we can define by creating a function called as gradient descent, and it takes multiple values x, y. We also need the theta, we need learning rate, and we need iterations that are required to run through this function. So that's what I need. So I'm going to first say m equal to length of y. I'll take that, and then for underscore in range of iterations. So for all the iterations that we have, I should say iterations, which makes more sense. So I'm going to run through this for loop for all the iterations that are there. So first I'm going to try to get my predictions equal to np dot and pass it x and theta. For errors, I will say predictions minus y, and for gradients, I will get 1 divided by m times np dot x dot t transform and errors is what I'm going to take. Let's look at it. Perfect. So that's our gradients, and then to calculate the theta for it, I'll have to decrement it based on learning rate times gradient. So that will give me my theta, and that's what I can return after this loop is over, going through the iterations that I've specified, and theta. So there you go. That's our gradient function. Now next thing is, let's create some sample data to test it out. Sample data, where I'm going to say x equal to np dot array. Let's create an array, and we'll also have to include the bias terms here. So for this, I am going to create 1 comma 1, the first element in the matrix, 1 comma 2, second row, and my third row I'll give 1 comma 3. Pretty simple and straightforward. Next, I am going to create the y variable, np dot array, and this is a one line or a single vector, 2 comma 2.5 comma 3.5. This is my y. Next, I need theta. For theta, I will say np dot array, and that can be represented as, we can do the initial parameters as 0.1 comma 0.1. Next, I will give the learning rate of 0.1 iterations. I don't want to give too much, but let's try with 1000. That's how many times this will run through this loop. Next, let's do the perform the gradient descent. So we have the function, why not run through it? So do that. I'll say my optimized theta equal to gradient descent, and now we'll get all the values that we have here: x, y, theta. We have learning rate of 0.1, and we have iteration of 1000. Let's call it iterations since it's 1000. And now let's print this out, see how our optimized parameters look like, and that I can say optimized theta. Perfect. So this is the entire function. So let's go ahead and run it. Now clear it out and say python day3 ex3.py, and our optimized parameters are 1.1663 and 0.7507. So it went through this bunch of different times, 1000 times specifically, and used the gradient descent function to give us the optimized parameters for the theta. Next, if you want to do some more additional practice on these, you can use SymPy to compute second order derivatives, which is Hessian metrics. So we did the first order derivatives, but you can do the second order derivatives if you want. You can implement gradient descent with multiple learning rates and compare convergence speeds. Also, you can visualize the gradient descent process on a quadratic function. To try this out and let me know how it goes. If you have any problems or questions or were not able to follow along, let me know and I'll get back to you. So to recap, today we explored the foundational concepts of derivatives and gradients, focusing on their applications in machine learning. By implementing the gradient descent, we gained practical insight into optimization, which is a key component for AI model training, and we'll be using that quite a lot in coming weeks. So let me know if you have any issues. Welcome back to day 4, Calculus for Machine Learning, where we're going to cover this time integrals and optimization. Now, the topics that we will start with is first understanding integrals and their applications in ML. So, what are integrals? Integrals compute the area under a curve, representing the entire accumulation that is under the curve. If you see a bell-shaped curve, that's where integrals come into picture, where it computes the area that is covered under that particular curve. The definite integral of f of x from a to b is represented as integration from a to b f of x dx. This is the formula. This is what you'll see probably, and you've seen in school before. Now let's talk about applications in ML. We have probability distribution. Integrals are used to compute the probability under a probability density function, which is PDF. Also, cost functions. Regularization terms in cost functions often involve integrals. Example, integrating over weights in Bayesian models. Let's look at some examples with Python of how to use it. So I'm going to go back, create a new file, Python file. Make sure I save it in day 4, call it day 4 underscore samples. And here first, we need SymPy as SP. That's the library we'll use, or module we'll use. And then I'm going to say x equal to sp dot symbol. I'll use the symbol x as before. If you have not seen the previous videos, I would recommend you watch them before doing this. And I say my function that I'm interested in is x square, which can be represented as x star star 2. Now definite integral, I'm going to give it definite integral equal to sp dot integrate. That's the function that we'll call, and to it we'll pass f and x comma from 0 to 2. So what I'm doing here is I'm saying integration of x square dx from 0 to 2. Now let's go ahead and get indefinite integral. Indefinite integral. For that, I am going to say sp dot integrate, and here I'm going to say f and x. So this is integration of x square dx. So I have that. Now let's print this. Print definite integral is definite integral. Do the same thing for indefinite integral, and the variable is this one. Let's look at it. Sure, we are in the right folder. Bootcamp week 3 day 4. Perfect. And I am going to run Python day 4 dot samples, and there you go. Definite integral is 8 by 3, and indefinite integral is x cubed divided by 3. So that's how you can calculate definite and indefinite integral. Next, let's look at some optimization concepts. So we have local versus global minima, where local minimum is a point where the function has a lower value than the neighborhood points, and global minimum is the absolute lowest point of the function across its entire domain. So in ML or machine learning, the optimization goal is to find the global minimum of a loss function, but local minima can sometimes suffice. Next, let's look at convex functions. A function is convex if, I'm going to display you the entire formula, where f of lambda of x1 plus 1 minus lambda of x2 is less than equal to lambda of x1 plus 1 minus lambda of fx2 for all lambda which belongs to 0 to 1. Now, convex functions ensures that any local minimum is also a global minimum. Next, non-convex functions in ML. Most of the neural network loss functions are non-convex, leading to challenges in optimization. Next, let's look at stochastic gradient descent, or also called as SGD, and its variants. So first, what is stochastic gradient descent, or SGD? An optimization algorithm that uses random subsets or also mini batches of the data to compute gradients and update parameters. So why do we use SGD? SGD is used for faster convergence for large data sets compared to batch gradient descent. Now, what are the variants of SGD? We have mini batch SGD, which updates parameters using small batches instead of single examples. We also have momentum, which adds a fraction of the previous update to the current update to accelerate the convergence. And we have Adam Optimizer, which is used quite a lot. It combines momentum with adaptive learning rates for faster convergence. Now that we know the basics about integrals and optimization, let's get into some hands-on exercise. So the first exercise that we'll be doing is we'll be calculating integrals of simple functions. The objective here is to use Python to compute definite and indefinite integrals, which we have seen earlier. And what we'll be doing is we're gonna define symbolic functions using SymPy first, and then compute the definite and indefinite integral. So let's go ahead and I'm going to create a new file, call it day4_ex1.py. Now to start with, we'll import the SymPy module and give it an alias of sp. Next, let's go ahead and define a function. Now this function, I'm going to say x equal to sp dot symbol, symbol, and I'll use the symbol x. Next, I'm going to say f equal to sp dot exponential of minus x. So we have x and f. Now let's compute indefinite integral. Now, as we've seen earlier, indefinite integral can be calculated by saying sp dot integrate and pass it f and x. Next, let's print it out. Print indefinite integral, comma, and print the value of it. Next thing, let's compute definite integral. To do that, I'll say definite integral equal to sp dot integrate and pass it f comma x comma 0 to sp dot oo. So that's what we specify for definite integral. We'll say print definite integral is equal to comma, pass the definite integral right there, some spaces so it looks good. So now let's go ahead and run this. I'm going to clear this out and I'm going to say Python day underscore, I forgot to give day 4, but it's the same name, and my indefinite integral is minus exp minus x, and my definite integral is 1. There you go. So we have the values as per expected. Our second exercise here is to implement stochastic gradient descent for a linear model. Now objective here is to implement SGD to minimize a linear regression loss function. What we will be doing is we'll be defining a simple data set and we'll write a Python function to perform the SGD. So let's go ahead and start coding. I'm going to clear this out, create another file, save it as day4_ex2.py. So first, let's import numpy as np. Next, I need to generate some synthetic data. So I will say np.random.seed. If you remember, this will make sure that every time we run the randomizer, it will give me the same data, same random data. So I'm going to say x equal to 2 times np dot random dot rand and I'm going to say 100 comma 1. So this is my feature. Now I want to create a target of which I'm going to predict. So 4 plus, I'm just giving some random numbers, 3 times x plus np dot random dot randn of 100 comma 1. So this will give me target with some noise values to it, added to it. Now let's add some bias term to x. To add bias term, what you do is let's create x underscore b equal to np dot c underscore and np dot ones 100 comma 1 comma x. So this is our bias term that added to x. Now next we need to get SGD implementation. So let's see how do we, so create a function first, call it stochastic underscore gradient underscore descent, and then this will take our usual parameters, the target, sorry, the feature, the target, the theta that we have to give, next, oops, theta, and then we need learning rate and the number of iterations or epochs is another way for saying iterations. I'm going to first take m is equal to length of y, do that. Next, I'm going to run the iteration for, I'm going to say epoch in range of n underscore epochs. I want to run this, and then again for I in range of m, which we calculated the length of y. And here I am going to say first I want to get the random index equal to np dot random dot rand integer I. So I'm going to pick a random index here. Oh, sorry, not I, but m. And then next I am going to say xi equal to x of random underscore index. So depending on what index I've taken, random index plus 1. So that will give me xi value. Similarly for yi, I will say y of random index colon random underscore index plus 1. Next I need the gradients. For that I'll say 2 times xi dot t at xi. So I'm doing multiplication here. Again multiplication theta minus yi. So there you go. This will give me my gradients. And for theta, I will say minus equal to, I'm going to decrement based on the learning rate times gradients. So that will take care of that. Now, finally, I can return the theta here. So that is the value of the final optimization. Now, next step is to initialize this parameter that I want to start with. Initialize parameters. So I am going to create theta equal to np dot random dot randn 2 comma 1. This is give me the bias and the weight. Next I have the learning rate, which is, I'll say 0.1 or 0.01. Let's do 0.01. How many iterations I want? Let's keep it 50. I remember last code that we wrote, we used 1000. Perform SGD now and get the, so we are calling that function above. So for that I'll say theta optimized equal to stochastic gradient descent x underscore b that you generated above y and theta, and we need to pass the learning rate and we need to pass the epochs. There you go. So I'll pass all these. That will let me get the theta, optimize theta, and I can say print call it by its name, optimized parameters are theta underscore op. So this should give me, so the expected result should be around based on, okay, I'm not going to even guess this. So let's go ahead and run this. I am going to say Python day 4 underscore ex2.py, and there you go. We have our optimized parameter 4.16 and 2.69. These are very close to the actual values that we have given, but that's how you can perform an SGD to get the optimized theta here. Now if you want to do some additional work, you can go ahead and visualize the loss functions surface and the SGD optimization path. Also try to implement a mini batch SGD and compare it with the vanilla SGD. And also finally, use Adam Optimizer for a more complex data set. And we'll be doing some of these in our machine learning videos in the future, but try it out and let me know how it goes. If you have any issues or problems, let me know. So just to summarize, today we learned the basics of integrals, optimization concepts, and stochastic gradient descent. By implementing these concepts, we gained a deeper understanding of optimization, which is a cornerstone of machine learning training. If you have any questions, day 5, probability theory and distributions. Let's start with probability basics. And in here, let's look at conditional probability. The probability of an event A given that event B has occurred is represented as P A by B, which means the probability of an event A given that event B has occurred is equal to P of A and B divided by P of B. Example can be the probability of drawing a red card given that a face card is drawn from a deck of cards. Next we have Bayes' theorem. This relates conditional probabilities where P of A of an event A given that event B has occurred is equal to P of B given event A has occurred, P of A divided by P of B, where P of A or probability of A is prior probability, P of B A is likelihood, and P of B is evidence. We can do this Bayes' theorem in Python by, let's create a new file, save it in day 5 as day 5 underscore samples. Now if I want to create a Bayes' theorem, I'm going to say Bayes theorem. So I'm going to create a function here, and to it I'll pass the prior probability. I'm going to give it the likelihood, and I'm going to give it an evidence which is based on our function here. And to calculate it, you can say return likelihood times prior probability divide by evidence. That's what we return. So that's the actual formula right here. So that's how Bayes' theorem works. Let's save this and close it, and let's go to the next topic, which is common probability distributions. Now we are going to talk about different probability distributions here, starting with the Gaussian distribution, which is also called as a normal distribution. It's a bell-shaped curve with mean mu and standard deviation, which is sigma. The formula for it is f of x equal to 1 divided by square root of 2 pi of sigma square e raised to minus x minus mu square divided by 2 sigma square. Now, example of this can be modeling continuous data like heights or test scores. We can look at a Python example for that. What I'm going to do here is I'm going to import first numpy as np. You can go ahead and comment these out. Next, I want to import matplotlib to plot a graph for this, pyplot as plt. So let's say if I use, say, mu for mu and sigma for sigma, and I'll set its value to 0 and 1. Next, I'm going to create a variable x equal to np dot linear space minus 4 comma 4 comma 100. Next I will say y equal to 1 divided by, it's based on the formula that we have here, and we need to pass np dot square root of, and inside square root we had 2 times np dot pi, as you can see here, np dot pi, and we need sigma square, so let's say sigma star star 2, which is sigma square, make sure all the brackets are closed, times np dot exp exponential, that's what we have here, exponential raised to minus, so that we can specify by saying np minus 0.5 star, because we have divided by 2 below, so that's why I'm doing that, minus 0.5 x minus mu, and after this divide by sigma, and then square the entire thing, as you can see from the formula right here. So next step is to plot this. So I'm going to say plt dot plot x comma y, and then I'm going to say plot dot title equal to Gaussian distribution, and then I'll say plot dot show. If you have not seen for some of our previous videos on matplotlib, that will probably help us understand what we are trying to do here. So now that I have it, let's run it and see how it looks like. I'm going to open terminal, make sure I'm in the right folder, week 3 day 5, and I'm going to run this file python day 5 underscore samples, and there you go, we have our Gaussian distribution right here. So now if you had the similar graph, that's good. If not, please check your code again to make sure that it's exactly same, because sometimes the formula can be confusing. As you can see, it has a lot of different parameters to it. Next thing, we're going to look at Bernoulli distribution, which describes outcomes of a binary experiment. Example, you can think of it as a coin toss. So the formula for that is more on p of x equal to 1 equal to p, p of x equal to 0 equal to 1 minus p. So this is the Bernoulli distribution. And now if you want to implement this, I am going to comment this out, and then here let's say p equal to 0.6 and plt dot bar diagram, in this particular case say 0 comma 1 and 1 minus p comma p are the two parameters. Color, I will use blue for this bar, and that's all that I need here. Next, let's give a title, call it Bernoulli distribution, make sure I get the spelling right, Bernoulli. Next I will say plot dot xtext is 0 1, and then I'll need labels, which is 0 for failure, and then I need 1 for success, which is 1 is for success. Perfect. So those are my xtext, and then finally show the plot. Save it, go back to my terminal, clear this out, and run this. And there you go, we have our Bernoulli distribution for 0 and 1 based on the probability of 0.6. It kind of shows it properly on the graph. Next thing that we want to talk about is binomial distribution. Now, binomial distribution models the number of successes in n independent Bernoulli trials. So this is kind of defined as p of x equal to k equal to n to k p raised to k 1 minus p raised to n minus k. Now, if I want to show this in Python, the way to draw this out is from cpy dot stats. That's the module that we'll use. Import, we need binom. That's where you can find the binomial distribution function. Let's say n comma p equal to, let's assign it some values like 10 and 0.5, x equal to np dot range from 0 to n plus 1. Next, I'm going to say y equal to, as I mentioned, we use binom dot pmf, and inside this I'll pass x, n, and p, the different parameters that it needs to run the binomial distribution. So once I've given that, let's plot the bar. Say plt dot bar x comma, do I have my plot is not commented, that's good, x comma y comma color equal to, last time we used blue, this time we'll use green. Next, I'm going to say plot dot title, and for the title I'll say binomial distribution, and then plt dot show. That's it. Let's go ahead, open terminal, and make sure my graph from the before is closed. Clear it out, run it again, and there you go. We have a binomial distribution which looks perfectly fine. This is how a binomial distribution should look like based on the values that we have provided. So if you got this, that's good. If not, please check your values and what functions you're calling. Or if you have an error, let me know and I'll get back to you. Next thing that we're going to talk about is Poisson distribution. Now, Poisson models the number of events in a fixed interval of time or space that is defined as p of x equal to k equal to lambda raised to k e raised to minus lambda k factorial. So if you want to define this or do this in Python, the way to do it is, I am going to comment this out. This is something similar. We'll use, instead of binom, we'll use Poisson. That's the module that we want. I'm going to say lam equal to 3. I will say x equal to np dot range, and I'll give values from 0 to 10. Next, I'm going to say y equal to Poisson and in dot pmf, and pass it x and the value of lamb, and then I'll say plot the bar graph where I'll say x is pretty much same as before, and next I will give so let's change the color this time to orange, and next I'll give a title. This time it's POI SSON, Poisson distribution, and show this plot. Perfect. Let's go back, clear it out, run it again, and this is how the Poisson distribution looks based on the lamb and x values that we have provided. Perfect. This is how it should look for you. If you had any issues or problems, let me know. If not, good, we can move to the next topic, which is applications in machine learning for all these different distributions that we have learned. So first, let's look at Gaussian distribution. It is used in Gaussian naive Bayes and kernel density estimation. We have Bernoulli distribution, which is used for by models binary classification problems. Example can be spam or not spam emails. We have binomial distribution, which is used in logistic regression to model binary outcomes. And we have Poisson distribution, which models the count data. Example can be number of clicks on a website. That's what it's used for. So these are different applications in machine learning for these distributions that we have learned. Next, let's look at hands-on exercise. So we will be doing a couple of them here. First one is to calculate probabilities using Bayes' theorem. The objective here is to write a Python function to calculate probabilities using Bayes' theorem that you learned earlier. So the example problem can be a disease affects 1% of the population. A test is 95% accurate for diseased individuals and 90% accurate for non-diseased individuals. Now what we have to do is find the probability of having the disease given a positive test result. So let me write it down so it's much more easier to understand. I'm going to create day 5 underscore ex1.py, and as I mentioned, the problem here is, let's create bullet points. I'm going to say first the problem is, I'm going to give 3 bullets for 3 different things that we're going to define here. A disease affects 1% of a population. Next, I can say a test that is available is 95% accurate for diseased individuals and 90% accurate for non-diseased individuals. And then the final one is, what we have to do is find the probability of having the disease given a positive test result. Because even if you're not, as I mentioned, the test is 90% accurate for non-diseased individuals. Okay. Oh, there's no more typos. Okay, so let's see. Let's go ahead solving this. So as I mentioned, we'll be using Bayes theorem. So first, let's create a function for Bayes theorem, which takes prior probabilities, which takes the sensitivity and the specificity. The spellings are right, hopefully. So the evidence is sensitivity times prior. If you remember the formula that it had, this is what it is, and 1 minus specificity times 1 minus prior. Okay, so that's the first line of our. Next, we can calculate the posterior equal to sensitivity times prior and divide by evidence. Now that is what we will return here. So let's say based on the requirements, our prior is 0.01, which means 1% prevalence. We have sensitivity is equal to 0.95, which means true positives are 95%, as it mentions. Next, we have specificity equal to 90%. So that's what we have. This is a true negative rate. So again, if I want to write it down based on a requirement, it's 1% prevalence. Our sensitivity, as I mentioned, which is also called as true positive rate, and our true negative rate is specificity, true negative rate. Okay, so now that we have this, let's go ahead and get the value. Posterior equal to Bayes theorem, and to this I can pass the values that I've created here. Prior, next it needs sensitivity, and then it needs specificity. Let's print it out. Now we say find the probability of having the disease given a positive test result. So probability of disease given positive test is posterior. So let's run this and test it out. I'm gonna make sure my graph is closed, clear it out, and I'm gonna say Python day 5 exercise 1.py. Probability of disease given positive test is 0.08, which is 8% probable that you might have the disease. So that's pretty cool. Now let's clear it out, and I hope you were able to figure out or calculate the probabilities using the Bayes theorem that we did here. If not, had any issues or have any questions, let me know. Next, let's go ahead and look at exercise 2. Our exercise 2 is to plot and explore different probability distributions that we have learned, which is Gaussian distribution, binomial distribution, and Poisson distribution. Let's look at those and how we can visualize and understand key probability distributions using Python. So go here and save it as day 5 exercise 2.py. Now here, first thing I'll say import numpy as np. Next I'll get my matplotlib dot pyplot as plt. Next import skypy dot stats, and import from this I can get my Gaussian distribution, which is also called as normal distribution. I need binomial distribution, so that is binom, and Poisson comes from POISSON, that's the Poisson distribution. So we have these. Next, let's start with Gaussian distribution. So here, the reason we see error here is to say from import these. Perfect. So for this, I'm going to say x equal to np dot linspace, and here I'll give -4, 4, 100. Next, I'm going to say y equal to normal distribution dot pdf, and in here I'm going to give x loc equal to 0 and scale equal to 1. Next, I will say pl dot plot, and I want to plot x comma y label equal to Gaussian or normal distribution, whatever you want to call it. Dot title, I'll give Gaussian distribution. So that's good. Next, I'm going to say plt dot show. So we'll show my plot. So let's go ahead and run it. I'm going to say here Python day 5 ex2.py, and there you go. We have our Gaussian distribution. Perfect. Next thing is binomial distribution, and this I can say n comma p equal to 10 comma 0.5. We have x equal to np dot range and pass it 0 comma n plus 1, and y equal to binom dot pmf, and it needs x, n, and p, just like how we did earlier. So these three parameters. Next, I'm going to say plot dot bar. It's a bar diagram that it gives. So let's give it x comma y and label equal to binomial. Next, I want to say title, and title will be binomial distribution. And finally, let's show this plot. Perfect. I am going to comment this out. So it shows only one right now. Close this previous one and run it again. And there you go. It showed both of them because I still have I'm using the same variable here. So I'll just go ahead and comment this out and close this and run it again. There you go. We have our bar diagram displayed here. You can always merge something like this. It's interesting to have bar and the plot diagram together displayed here. Next one that we have is Poisson distribution, and for this we'll say lamb equal to, so we need lamb and x, y, lamb equal to 3, x equal to np dot range. I will say 0 to 10. Next, I need to give y equal to Poisson here dot PMF, and this needs X and lamb values to it. Perfect. Now let's create the bar diagram, bar chart. I'll say X comma Y, and I need label equal to Poisson. Perfect. Next, I need to give a title. I mean, I don't need, but it looks good. SSON distribution. Next, let's show the plot. This is bare minimum. You can always give X and Y axis and all those things, but I like to keep it as simple as possible. I'm going to close this binomial distribution, clear it out, and run this one. And there you go. We have our Poisson distribution displayed here on the graph perfectly. So I hope you are able to follow along. If not, go through this and let me know if you have any issues or problems. For additional practice, you can look at creating and visualizing a multinomial distribution for multi-class data. You can try with comparing Gaussian and uniform distribution for continuous data. Also, try to use probability distributions to simulate and analyze real-world data sets that are available in different websites. So to summarize, today we explored probability theory and its applications in machine learning. By calculating probabilities using Bayes' theorem and visualizing distributions, we gained an essential understanding of probabilistic modeling, and this will be quite helpful in future videos as in we go along. So, Day 6, Statistics Fundamentals. Today we are going to look at measures of central tendency and dispersion. Now, what is central tendency? Central tendency has mean in it, which is the average value of a data set. It has median, the middle value where data is sorted, and the mode where the most frequently occurring value. Now, if you want to kind of look at these three in Python, we can probably start a file, save it as day6 underscore samples, and here I will start with first some data equal to, let's say, 10, 20, 30, 40, let's take one more 50. So we have some data. Now mean is equal to sum of data divided by length of this data. That's how you calculate mean. Let's print it out. Print mean comma mean. If I open my let's say Python day6.samples, and there you go, mean is 30 of this data set, 10, 20, 30, 40, 50. The mean over here is 30. So that's how you calculate the mean. Now let's look for median. Now median, as you're familiar with or for not, needs sorted data. So I am going to say sorted data equal to sorted, and sort the data that we have above. Next, to calculate median, I'm going to say median equal to sorted underscore data, and in here I'm going to say length of data / 2 if length of data mod of 2 is not equal to 0, else next line I'm going to say sorted underscore data length of data, I'm in the right place, / 2 minus 1 plus sorted data length of data / 2, and then I will say close / divided by 2. So that will give me the median for this entire value. So to calculate, to actually print it out, I'm going to say print median of the median. So again, this will be the median of this entire data. Again, it's already sorted, so we don't have to sort anything. Let's go to our here and print it out. There you go. My mean is 30, median is 30 because it's a pretty uniform data that I have here. So that's why it calculated it and gave me that median. Next that we have is mode. Now for mode, we need something from a library. I always like to put my modules up here and say statistics. I need mode. So for mode now, very simple. I'm going to say sprint mode. I wish everybody had the libraries, but there are different types of libraries available for doing this. But I can say from statistics, I can just say mode of data and then go ahead, clear it out, print it out again. So mean is 30, median is 30, mode is 10 in this particular case from the data that we have. Next, let's look at dispersion. So we have variance inside here, which is the average squared deviation from the mean. And if you want to calculate variance in here, you can say variance equal to sum of x. This is the function for it. This is the algorithm for this, or let's say formula for this, 2 for x in data slash length of data, or divide by length of data. So this is what will give you variance. Now if I want to print this out, let's go and print variance comma variance for the same data that we have. Let's look at the differences, clear it out, run. We already know the first, and the variance is 200 for this data that we have. Let's make sure everything is right. X minus mean square of 2 for x in data length of perfect. So that's the variance that we get. Next thing that we can calculate is standard deviation. Now standard deviation is the square root of variance indicating the spread of the data. So we already have variance, so I can do the square root. I can say std deviation, standard deviation equal to variance square root. So for that I'll say square of 0.5. This will give me standard deviation. Comma std underscore dev. Let's go ahead and print everything together. There you go. My standard deviation is 14.142133, whatever the rest of the values is. But those are the difference basic or measures of central tendency and dispersion that we have. Next, let's look at hypothesis testing. Now, what is hypothesis testing? It's a statistical method to determine whether a result is significant or occurred by chance. So the steps that we follow for this is, first we formulate the hypothesis. We have two different things here. One is null hypothesis and the other one is alternative hypothesis. Null hypothesis, you'll probably always see it as defined as h of 0, and alternative hypothesis is defined as h of a. Now null hypothesis assumes that no effect or difference is created, whereas alternative hypothesis assumes an effect or difference exists. Second step is to calculate the test statistic, which quantifies the difference. Next, we determine the p-value, which is the probability of observing data as extreme as the test statistics under null hypothesis. And finally, we interpret the results, where we check if the probability is less than alpha, which is a significance level, example 0.05, we reject the null hypothesis, which means it has some significance. Example for this can be the comparing mean test scores of two groups using a t-test. Next, let's look at the confidence intervals and statistical significance. Now, confidence interval. It's a range of values within which the true population parameter is expected to lie. The formula for this confidence interval is Ci equal to x bar plus or minus z times s divided by square root of n, where x bar is a sample mean, z is the z-score, example 1.96 for 95% confidence, and we have s, which is standard deviation, which we already learned how to do. If I want to do this in Python, let's go here and comment everything out. Let's go all the way to the top, and here I am going to import something from scipy dot stats as stats. So from the scipy, we got stats from there, which has all the different methods available for statistics. I'm going to say mean equal to mean, sample mean equal to mean. Next, I'm going to say z underscore score equal to 1.96. Now, where do we get this mean from? We got the mean from here. So I'm going to get this data right here. Okay, so we have our mean, we have a z-score, which is 95% confidence level. Now to calculate CI, we can say sample mean minus z underscore score times standard deviation, std underscore deviation, divide by length of data times 0.5. Now that we need most of this, looks like, so if we need the std deviation, that is coming from here. I'm going to take this, and for that I need variance, which is sum of x minus mean, and we already have mean, so I'm going to take that up here. So we have variance sum of x minus mean, and I think I don't need to print this, need the standard deviation for this. Perfect. So I have that. So next thing that I need is comma, not here, comma, and I need sample mean plus z-score as per our formula that we saw times std dev divided by length of data square root, so 0.5, so that should be perfect. So this will give me print 95% confidence interval is the CI level. So I'm gonna display that. Let's go ahead and run this. Confidence level is 17.60, 42.39. That's pretty good. So that's our 95% confidence level that we have. Next, let's talk about statistic significance. A result is statistically significant if the p-value is less than the significant level, which is alpha equal to 0.05. So now that we have completed some of the basics and some understanding about confidence intervals and statistic significance, let's look into hands-on exercises. Our first exercise is to calculate mean, variance, and standard deviation. So if you've already followed along, you can skip this, but the objective here is to compute the basic statistic measures for a data set. So I'm going to go ahead and use some shortcuts this time. I'm going to go back here, create a new file, save it as day6 underscore exercise1.py. And as I mentioned, I'm going to import numpy as np. And I'm going to have a data set. Let's call that data set as data equal to, I'll use the same data I used before, 10, 20, 30, 40, and 50. And then I will calculate the stats. First, I'll do mean, then I will do variance, and then I will do standard deviation. So if you know the formulas, go ahead and write it and pause it here. If you don't, I am going to do it here and follow along. Data, I can say np dot variance data. As I said, shortcut. It's easier to just write it instead of writing the formulas, because these are available through some of the modules that Python provides inside NumPy. So we have all the data available here. I am going to say print mean is mean. Next, I want to print the variance. comma variance. Next, I want to print the standard deviation, which is std underscore dev. So I have these. So that's our exercise. Let's go ahead and run this. I'm going to clear this out and say Python day underscore ex1. Looks like I've missed the day 6 again. But here's my mean, variance, and standard deviation. Looks exactly same as what we got from using the complete formulas earlier, but now you have np.variance and or numpy to do all these things for you. Next, our second exercise is to perform a t-test. Now we'll perform a t-test to compare two sample data sets. So let's go ahead and first have those sample data sets. I'm going to save this, go next and save it as day6.ex2.py, use underscore, and from first I need scipy dot stats. From there I can import the t-test individual here, this one, and I need my sample data sets. For that I'll create two groups. One is group 1 with data of, let's give some random numbers, 2.1 comma 2.5 comma 2.8 comma 3.0 comma 3.2, and then I'll create a group 2 with data sets, that's 1.8 comma, I'll say 2.0, 2.4, 2.7, and give 2.9, some random numbers. Next, let's perform the t-test on this data sets. So for that I'll get t-stat and p-value from t-test underscore ind, where I can pass group 1 and pass group 2. So this is as straightforward as that. And here the t-stat is my t-statistics. So that is t statistics statistic, and that I can display by saying t underscore stat. Similarly, my p-value is this. You can print that out. Next, let's also do the interpretation, the statistical value for it. I'm going to say alpha, which was our, if you remember in the previous slide, we say statistical significance. If in statistical significance, a result is statistically significant if the p-value is less than the significant level, which is alpha is 0.05. So let's go ahead and do that. I'm going to say alpha equal to 0.05. Now I'm going to check if p-value is less than alpha, which means I'll print saying reject the null hypothesis, which means it's significant difference. Else I will say print fail to reject the null hypothesis, which means no significant difference. Let's see, I've given some random numbers, so let's see how does this act. You can try out with different values. I'm going to say Python day6 underscore ex2.py, run it, and it says failed to reject the null hypothesis, no significant difference, because the p-value is 0.2, whereas so my p-value, which is 0.2, is less than 0.05, and that's why it failed to reject, or greater than that, that's why it failed to reject the null hypothesis, because there's no significant difference. So I hope it was helpful to understand whatever we learned to implement in the code. If you had any problems or issues, let me know and I'll get back to you. For additional practice, you can try to visualize the distribution of data and highlight mean, median, and mode using matplotlib. You can perform hypothesis testing on real world data sets. Example, comparing exam scores of two groups. You can get these data from different websites, and you can calculate confidence intervals for proportions in a data sets. So just to summarize, today we learned statistical fundamentals focusing on central tendency, dispersion, hypothesis testing, and confidence intervals. By performing calculations and hypothesis testing, we gained hands-on experience with data analysis and decision-making techniques. And these are very important for some of the Day 7, Math Driven Mini Project or linear regression from scratch is what we're going to do here. So there'll be three different things that we need to learn before even starting this. First is applying linear algebra, calculus, and statistics. So for linear algebra, linear regression aims to fit a line or hyperplane to minimize the error between predictions and actual values. The mathematical model for this is y cap equal to x times theta, where x is the feature matrix with bias term, theta is the parameters which are weights and bias, and y cap is the predicted values. For calculus, we need optimization of theta which involves minimizing the loss function. That is defined as j theta equal to 1 by 2m summation of I equal to 1 to m for y cap I minus yi squared. And also the gradient of j theta, which is del or nebula of j, equal to 1 raised to m, 1 upon m x raised to t x times theta minus y. Next, we also need statistics. Metrics like mean squared error, MSE, and R square are used to evaluate the model performance. So we're going to look at each one of them in more detail. So first is using gradient descent for parameter optimization. Now the gradient descent algorithm goes something like this, where it iteratively updates theta using theta equal to theta minus alpha times del of j, where alpha is the learning rate and that controls the step size. The key steps involve initializing the parameters using theta, then we have compute the gradients, which is del of j, and update parameters using the gradient descent rule. Finally, let's talk about evaluating the model using the statistics metric that we mentioned. So we need mean square error, which is MSE, which is defined as 1 raised to 1 upon m summation of I equal to 1 to m y cap I minus yi squared, which measures the average squared error. And then we have r squared, which is r square equal to 1 minus ss res divided by ss tot, which measures how well the regression line explains the variance in the data. So let's go ahead and do our hands-on project based on whatever we have learned on linear regression from scratch. We'll be following three different tasks. Task 1 is to implement the mathematical formula for linear regression. Next, we'll use gradient descent to optimize the model parameters. And third task is to calculate the evaluation metrics. So for task 1, so let's go ahead and first create a project. I'm going to create a new file, save it in my day 7, and I'm going to call it mini project, which is linear regression from scratch. So first task, as I mentioned, task 1 is to implement the mathematical formula for linear regression. So the objective here is to create a function to compute the predictions. So let's go ahead and write some code for that. For that, I'll say import numpy as np. Of course, we're not going to do all the work here. We'll use some of the libraries that are available. And I will create a predict function which will take the x, which are our features, and the theta here, and we'll predict by returning np dot, and here I'll pass x and theta. So that will take care of predicting for me. So this will, that's all we need to do for task 1. Task 2 is to use, let's see, use the gradient descent to optimize the model parameters. So use gradient descent to optimize the model parameters. So here the objective is to implement gradient descent to minimize the loss function. The example, so code can be written something like this, where I can say gradient descent, and it takes, as we've done before, x, y, theta, learning rate, and iterations that are required to get optimized solution. Now I'm going to say m equal to len of y, and I'm going to go through each and every iteration here. For underscore in range of iterations, I will go ahead and get the gradients first. Gradients equal to, from the formula that we saw, 1 divided by m times np dot x dot t. This is the summation thing that we did. Np dot and to it I'll pass x and theta, and I'll put this entire thing inside a bracket, say minus, or right here, np dot minus y. Did I close all of them properly? No, one more. So yeah, that's my entire formula for that. Next I need theta minus equal to learning rate, so this will give me the optimized value, times gradient, and that's good, and that will return back finally the theta value. So I have that. And finally task 3 is to I think, look at it, calculate evaluation metrics. So I am going to say calculate evaluation metrics. The objective here is to implement functions to calculate MSE, which is mean square error, and R square. So the code for that, I can just say mean underscore square underscore error, which will give me with true values y and y predicted values. So I can calculate the mean square error from there, and this will return np dot mean of y underscore true minus y underscore pred and square root of the square of 2. So that's what I'll get here. And next, for our r squared, I'm going to say define r squared y underscore true comma y underscore pred, and to create this I need ss res first, if you remember the formula from before, and this will be ss res equal to np dot sum y underscore true minus y underscore pred and squared. So that's what I'll get. Next I need ss underscore tot, which is np dot sum, and this I'll give the same values. Actually y underscore true it needs, but it will be np dot mean of y underscore true, and here I'll square it. That's the ss tot. Now to bring everything together, 1 minus ss underscore res divided by ss underscore tot. Give it a little space, and that was our formula, if you remember from here. 1 minus ss res upon ss stored. So that's the r squared. So that's perfect. Now to put all of them together, let's start from the top. I'm going to generate some synthetic data. Some synthetic data. np dot create a random seed, my favorite number 42, and x equal to 2 times np dot random dot rand 100 to 1. So create some random values. Y equal to 4 plus 3 times x plus some bias np dot random dot rand n 100 comma 1. So there you go. So we have that value. Next I want to create add bias term to the feature matrix. Add bias term to feature matrix, and that I can do by creating a variable x underscore b equal to np dot c underscore, and here I'll say np dot ones 100 comma 1 comma x. So this will add bias term to our feature matrix of x. Next, let's go ahead and initialize the parameters that I need theta, I need learning rate, and I need iterations. Let's start with iterations. Let's do 1000 iterations. Learning rate, let's say 0.1, and for theta I will use np create a random one dot random dot randn and pass it 2 comma 1. So that initializes my parameters. Now next step is, actually we need the predict function, so which we already have. We have the gradient descent, we have the mean squared and r square. So let's go below and perform the gradient descent. To do that, we've done it before in the previous videos. Theta optimized equal to, call this function that we have written, pass it x underscore b, pass y, pass theta, we'll pass the learning rate, and we pass the iterations. So that's what our function needs, the gradient descent needs, and that's what we have passed. So once we pass this, okay, I think there is some problem here. I called it iterations and iterations. So Visual Studio Code kind of shows you what issues you have before even you face any problems. So that's good. Next one, I'm going to do predictions and evaluations here. So to predict, I'll create ypred equal to, call the predict function, pass it x underscore b, and we'll pass the theta optimized. Next, MSC to get the mean square error. Since we have ypred now, I'm going to call the mean squared error, pass the original target values and the predicted values. There you go. Next, to get r square, I'm going to say r2 equal to r underscore squared, call that function that we wrote earlier, and pass it y underscore pred. Perfect. And next, now finally we can print all the three of these. I can say print, first one is optimized parameters, which is theta, is r theta optimized, which we get from line number 44 right here. Next, I want to print, let's see what is the mean square error, MSE, which I can get from MSE. Next, I want to print the r square, so I'll say r square, that is comma r2. So that will give me my r square error. So let's go back here, clear it out, and say python mini project.py, run it, and there you go. We have our Optimized parameters, which is as long as it's between 4 and 3, that's good. So 4.2 and 2.77. Mean square error is roughly 0.80, and our R squared is 0.76, which is pretty good. So by completing this project, we have gained a thorough understanding of linear regression, gradient descent, and evaluation metrics. We also learned how to implement machine learning models from first principles using Python. So we did everything from scratch, which is pretty awesome. And I hope you were able to follow along. If you had any issues or any problems, let me know and I can help you out. If you have any suggestions or anything, let me know about them too, and I can add that to my videos. So I hope you were able to finish our week 4 with all the different projects that we have done. If you have